Today I will tell you a little bit about what we have been doing on these interfaces in high-energy batteries. And magnesium and aluminum and calcium are, of course, some of these choices. Here you can see the campus of the university where I sit at. You can see also that it's a very young university. It's only 20 years old. It's located in the southwest of Norway. So if you're ever in this part of the world, maybe on vacation, doing a lot of hiking in Norway, just send me an email and come by the campus that is also located very nicely in the fjord. So we have a nice view of the sea there. So I will be talking about interfaces, but before that, I would just like to stress once more that for any kind of electrochemical energy device, we need to think about the electrolyte, right? So from the solid-state chemistry perspective, we are interested in finding these two end materials that will give us the highest difference between the chemical potential so that we can extract the highest potential, and with this also highest power. So this is something that we have been doing, I guess, in the last 20, 30, 40 years, trying to find these matches of materials to make high-power devices. But then the reality kicked in, and the reality is typically kinetics. That means we need to move those ions from one side to the other, and we need to move it through an electrolyte separator and interphases. And so this electrolyte started being a big problem, or a kind of really important part of it, because in principle, it also defines the kinetic losses of this open circuit potential. But we know that works pretty well, so these deviations are not really high in most of the devices. But it determines the possible speed of charging and discharging. It determines the quality and pertinence of interfaces. It determines overall safety. So if you're interested in reading one of my favorite books about electrolytes, that would be this one, that is nowadays very hard to find because it is not produced anymore. But if you're interested in physical chemistry of interfaces, I would in any case point you to this really nice book. So, okay, the electrolyte is important, not only end phases, but where are we at now? And since I am an associate professor in battery technology, I get asked a lot of questions. It's a ubiquitous technology of nowadays, so people ask me, what is the next hype? And also, where should I invest my money? So if people ask me these kind of things, I try to show them a Ragon plot of different kind of battery technologies where you can see all the different zoos. This Ragon plot was plotted by a scientist that was interested in all solid-state battery. So you can see that the volume of this all solid-state batteries is the highest in this Ragon plot. It's a little bit biased Ragon plot. But in any case, you can see that we can either aim at high specific energy or at high specific power, which is where these all solid-state batteries stand. But if we think about the magnesium, it would be somewhere here with kind of relatively high specific energy together with lithium sulfur and lithium oxygen batteries. So what is to be done? This would be the kind of word bubble of what we are trying to do nowadays. Touch upon sustainability, performance, lifetime, availability of materials, but finally also cost, because the cost was driving the fact that we are producing this technology nowadays if we look at basically the cost of lithium-ion batteries over years. So what do? We follow the new or old directions. So the new direction would be simply diversifying out of sustainability and availability reasons. But of course, we are always interested in performance improvements, and then we go back to lithium metal and maybe try to work out the other metals with two electron reactions to get the highest performance possible. So that would be, I guess, what we are all doing nowadays in terms of improving battery technology. So what about these interfaces? If we look at our metal, in order to make these kind of high energy, high power cells actually work, we need to make these metals work. And if we think about what is happening there, in the case of lithium and sodium, the biggest problem is this continuous solid electrolyte interface growth. These are non-thermodynamically stable materials with almost anything in contact. So we will have a consumption of electrolyte and simply end up with a dry cell after a period of time, after we've reacted all of our interfaces. Then in some cases, we have this dendrite growth. This is why the first lithium metal batteries were retracted from the market. From the previous talk, we have heard that in the magnesium case, that seems not to be the biggest problem. But in any case, we do have some kind of non-flat electrodeposition. So some people deal with anodeless morphologies and cells where we are trying to kind of avoid non-flat deposition by having already porous current collectors. And so how do we deal with these two biggest problems? Well, we try to build artificial SEIs. We have already heard a little bit about it. And we try to tune maybe cationic transference number in order not to have this kind of dendrite growth. What we end up with at the end is this dead electrode mass, volume expansion, rough surfaces, and void formation that are in a way non-avoidable in these kind of materials. So I don't think that we have a very direct solutions for these kind of problems. So we have to even figure out if we can describe them properly in the next years. So what about magnesium? This is a very general sketch, and it applies or does not apply in very specific questions. So today I will also try to tackle or think, can we have a general thought on these kind of alkali, alkaline, earth metal electrodes, or do we really have to deal with physics and chemistry of each specific case? So maybe that's an open question for the discussion. Also, on your opinion, what do you think? Is this possible or is this not possible at the end of my talk? But special considerations for magnesium, I guess you have seen this kind of sketch many, many times. In the case of lithium, generally on electrodes, we have an SEI that is an ionic conductor. So we can transport lithium through it, and we hope that it's not too resistive, so we do not have too resistive interfaces that are making problems in our cells, but in principle, we can transport lithium. In many cases, if we have a magnesium metal, we simply cannot get magnesium through it. So people call it a passivation. I would call it simply a very, very ionically blocking interface. So somehow we have to figure out how do we solve this. And then there is another problem, and that is that in the case of our ideal SEIs, we always imagine it to be a dense, very thin layer because the resistance should be relatively low. But in the case of magnesium anode, we have heard a lot of different kind of things happen on those interfaces. Either we start with this kind of passivation, where we kind of chip parts off it, so dissolution. We have, there is quite many papers talking about dissolution of the SEI, but there is also quite many papers, in particular the old Auerbach papers, telling us a lot about absorption. So the processes are even more complex. We have some very complex species in our liquid electrolyte, and these get absorbed on the surface of magnesium. So the situation seems to be way more complex than in the case of lithium metal. So look at these kind of surfaces of the metals. They all look kind of the same. So for the ones that worked with these kind of metals in the lab, they of course tactilely know that these have very different hardness, first of all. So for the people that had to shape their calcium electrodes in the glove box, I am saying hi to your hammer hands, right? So it's much, much harder. Magnesium and calcium are much, much harder than lithium and sodium. So in the case of sodium, we can really nicely shape it, roll it as a kind of a cake and cut it out, etc. But in the case of magnesium and calcium, these are much, much harder. But their surfaces seem to appear quite similar if you get them highly pure and open them in a glove box, yet we do somehow expect that they behave differently. So there is not much, or there is some understanding of how these native oxide films form in our atmospheres, and our atmospheres are continuously under argon. Hopefully no oxygen touches these surfaces, and we cut them in the glove box. But we tried recently to also understand what actually happens with lithium and sodium in dry air. And in this specific case, we see a very big difference between these two. So in the case of lithium, we have this kind of very shiny surface of lithium in dry air. And in the case of sodium, we already see some opaqueness forming even with the naked eye, right? So naked eye is not, of course, the same as any kind of spectroscopy. But in order to do any kind of spectroscopy, we also have to move that metal to whichever measurement instrument we have. And so we have kind of understood that moving these metals, in particular in the case of sodium, is non-trivial task. Many things may happen on the way, even if we have very airtight transfer tools. So yes, here with the naked eye, we even see the difference. And we can see from AFM images that are also done, of course, in argon, in a glove box, that the roughnesses of these surfaces will, of course, also differ. And if we go to the molecular level, we can try to imagine that these kind of oxide surfaces are also different. So in the case of lithium, we have a dense layer of lithium oxide on top of lithium, while in the case of sodium, we can have both oxide and superoxide. And these might, from the starting point, also build more porous structures. So if we now think that we have actually such a metal with some kind of native oxide film on top, and then we contact this with our liquid electrolyte, of course it is relevant what kind of termination we have, and of course it is relevant, is this really porous or not, and continuous film. So this is just a kind of a note to ourselves to think about these things. Of course, it's really difficult or almost impossible to test every single foil or every single electrode that we have, but to kind of have in the back of our minds that these can determine not only the performance of our every metal electrode, but the performance of every single half cell, because we are using these metals as reference electrodes in our half cells. So that means that these kind of effects, the growth of interfaces, the consumption of electrolyte, can really affect our half cells, right? So on one hand, it is relevant both for application, if we are trying to solve these problems on metals, but on the other hand, sadly, it is also very relevant for our half cells if we are looking at our cathode materials. Okay, so how can we think about the SEI growth on these metal anodes? I personally can imagine two different kind of mechanisms. One would be we have either these kind of native oxide layer film, or we have some kind of initial passivation film on top of the metal electrodes. And this film contains either some kind of electronic conductivity or reactive radicals, and then we have a growth of an SEI from the solid-solid interface. Or we end up already with a porous film, which can be, again, a native oxide film, or anything that decomposes in the very instant we contact our metal with a liquid electrolyte. And then we have an anion or solvent diffusion through this pores, and then a contact at liquid-solid interface where the growth happens. And in this case, my SEI is drawn as one material, but we of course know it's actually a very complicated, nanostructured, inorganic, organic material in which we don't even really know if the specific phases are crystalline or amorphous. So we are still interested in knowing this. So how can we study this material? It has been studied with very many different techniques. So if we want to know the thickness of this material, we can try to cut it through with FIB-SEM and see it. But again, we have to do this ex situ. We have to first transfer our material to a SEM, and then we have to know really well how to cut it properly under not so high energy so that we can preserve these interfaces. So this is also problematic, both from the point of ex situ experiment and on the point of changes upon cutting with our beam. On the other hand, we can do some spectroscopies that we know from the spectroscopies of thin films. The most typical one that is used in battery community is XPS. However, XPS, if you ask thin film people, they will just start pulling their hairs out because it has been actually developed for very flat, thin films with very ordered structure, not containing all of these messy phases, not being very rough as we know it. And since we know that the beam in the XPS, once we spatter with argon, has a certain angle, imagine you have a very high roughness of your SEI, and you're starting spattering in the angle, so you don't know what you're looking at once you spatter. Also, if we know that this is could be amorphous or soft materials, if we spatter with argon, we are just embedding everything deeper. So we're basically, with our experiment, doing more of a kind of a messy thing than what we are trying to elucidate. So this is the big problem with the XPS, in particular if we have very rough interfaces. The same or similar is with TOF SIMs. This is energetically even more complicated. We are also shooting our interface with something. So this is also one of the reasons why we kind of went back to the basics and tried to use impedance spectroscopy, which is an electrochemical method that is an in situ method. So we are building a cell. We do not have to open it afterwards or transfer the materials anywhere else. We can work close to OCV, meaning that we can apply very small potentials and still look what is happening with our material. And in this case, impedance is quite a nice but useful method because we always end up with such a semicircle in a Nyquist plot, which is in the kilohertz range. So it really we directly, in a way, see the SEI contribution if we have a symmetric metal cell. So when we have this SEI contribution that is very well defined in a semicircle, what we could do is then either look at the evolution of this resistance in time or look at actually the activation energy of this process. This is not new. This is something that is known from corrosion since the 70s, and it's also something that Doron Auerbach did very extensively in the 90s on lithium metal. So what do we see from these kind of experiments? First, to see that we can actually very, very nicely distinguish different contributions of, in the first semicircle of the bulk, in the medium semicircle of the interface, and then the lowest part, it's actually the Warburg diffusion, where we can extract the transference number already from the bulk. So if we have these, and if we can actually measure the activation energy of these three different processes that are in series, and we know what the activation energies of typical materials are, because we have also studied this for the last 30 years. So we know that for liquids, our typical activation energy is around 0.1 electron volts. And in the case of SEI parts, these are solid state, and we know from their defect chemistry that their activation energy is around 1 electron volts. Then we can actually see where do our interfacial activation energies lie. So in the case of this symmetric lithium-lithium triglyme, we see an activation energy that is around 0.7 electron volts. So it's somewhere in between the 0.1 and 0.7. This is very similar a type of data that Auerbach also saw in the mid-90s. His conclusion after seeing this data was, well, this has to be a relatively dense SEI, but that SEI seems to be more conductive than its ingredients. Why is that so? Well, since we could not directly measure it, he had to start to speculate. So he speculated a couple of things, one being space charge zones at the grains of these specific compounds. So there is, for whichever reason, high conducting pathways in the space charge zone, or amorphicity, and for whichever reason, the amorphous materials are more conductive. But there has not been any direct evidence that there is space charge zones in the SEI. We have never measured it. So that states, since mid-90s, as a kind of a red thread throughout, the SEI is a special material. Each component is not particularly conductive, but for whichever reason, it's very conductive material. I am here trying to explain that in the case of sodium, we get an activation energy that is around 0.2. It's almost the same as typical liquids. It's the same what we get for a liquid electrolyte. So we tend to believe that that activation energy is a direct indication of liquid channels through the SEI. So in the case of sodium, we actually can see that also with FIB-SEM. These SEIs form very quickly, and we can even see that this porosity is quite big. It's hundreds of nanometers of pores. But in the case of lithium, it is not very easy to see it, and the contribution of the liquid pathways is much smaller than in the case of sodium. So in my opinion, this is the reason why we have never thought that this could also actually be porous since the mid-90s. So, okay, if we look at what we have seen with this kind of impedance spectroscopy analysis, the most interesting part is indeed this, that we see in the case of sodium with triflate and triglyme electrolytes, liquid pathways at the very beginning when we assemble the cell. So this is how the FIB-SEM looks like. But then after long-term aging, we see, this is 600 hours, we still see that the activation energy is around 0.6. So it means it has not densified yet. We are still far away from the lithium case, in particular in the carbonate electrolytes. So there are still some liquid pathways. How are these liquid pathways distributed? We don't know. This could be also an isolated liquid in a solid electrolyte. It is not excluded. But it is there. On the other hand, with the lithium, we can see that we have a change in different kind of growth modes. So for the ones that maybe know a little bit more about how the SEI growth modes are typically considered, we typically have this kind of long-term square root T dependence of growth. And this is something that we also see for long-term lithium growth in symmetric lithium cells. But in some specific cases, this is a diffusion-controlled growth, but we sometimes see even this linear surface control growth in the case of lithium. This is not something that you see for every electrolyte under every circumstances, but in principle here we can see it in short term from 0.4 to 4 hours. And then the very initial studies on magnesium, we have only seen something quite strange, and that is that the resistance of our SEI actually drops in time. So this is a specific type of electrolyte. It's a liquid-solid electrolyte in contact with magnesium. And we simply, instead of these kind of square root T growths, etc., we see just some kind of drop of resistance in time. And we could say, okay, this is maybe mechanical instabilities or dissolution that we already talked about. But we did not know in detail what is happening here. So I can just invite you to see Mario's poster today in the evening, because he will be showing a little bit of what he has done when he visited me in Stavanger on magnesium and aluminium. So this is unpublished data, and talk with Mario about the details tonight. But what we have looked at is kind of two typical magnesium and aluminium systems. Again, symmetric cells. So here we have a Grignard, and here we have this ionic liquid electrolyte. And what we see, as we typically see in magnesium, is this really high resistances of the interfaces. So this looks quite horrible. It's every electrochemist's nightmare. In particular, if you do a lot of impedance spectroscopy, you see a lot of features happening here. So it's not this beautiful one semicircle with a very nice defined capacity, right? So it's it tends to be more complicated than that. So in this paper, we also try to elucidate a little bit of these kind of features in impedance, but I'm not going to bother you too much about it because it's very nerdy impedance stuff. What I can tell you is that if we look at the activation energies, we see at the beginning that it's around 0.4. So we are, again, somewhere in between the liquid and the solid state. So it's not very liquid, it's not very solid, it's really in the middle. But with the time, at the end, here the end is something around 47 hours, we see that this activation energy gets lower. So we are actually getting more porous SEI in time. Not as in this situation with lithium and sodium where we are actually densifying it. That is, again, maybe a confirmation of these dissolution mechanisms that I was talking about, but also about this kind of complexity of adsorption and desorption mechanisms. So how do we study that? We would have to have some kind of operando methods to really know what's happening on that interface. In the case of aluminium, it's the same, more or less. In the case of aluminium, it's also known that these kind of electrolytes are quite corrosive towards the native films of aluminium. So it's quite interesting that in this case, again, we go from 0.8 to 0.25 electron volts. So interesting findings in magnesium and aluminium, very, very different than the lithium and sodium cases. So please go and talk with Mario. What we also see in this case is that mechanical activation, this is how we call, this is our nice name for scratching of your magnesium electrode surface. I don't know how many of you do that when you assemble the cells. So we show that this mechanical activation is not really beneficial. We see more or less the same resistances. So yeah, it seems that not to be so relevant to do. Okay, so I have shown you a lot of impedance data, and most of you, and this is also a question that I get on conferences all the time, is how do you actually fit those data, and does this make any sense at all? And what can I see from this data? What kind of fit is actually meaningful? I'm interested in physical models. I'm a chemist, so I'm not a chemical engineer that likes to look at parametric models and get a lot of numbers from it. I'm a physical chemist, so I'm interested in physical-chemical models. And these are kind of two extremes of these physical-chemical models that have been suggested by some great people in the field. On the left side is a sketch from one of these 90s Auerbach papers. I really love this paper because it's very, very detailed. But the model that is presented, I guess we have already left it behind in the 90s. And that model shows that we have a lithium surface, and then we have a number of layers on top of each other, ending up with a porous layer at the end. And so the equivalent circuit is basically these layers in series. So anyone who has tried to fit an impedance spectra knows that the more things I add in series, the quality of my fit actually improves. So it's not actually it's not a bad thing that we are adding this. This fits into the impedance data, but we now know that our SEI is not layers on top of layers. This is really complicated, interdigitated material. So we have dropped this kind of way of seeing things. And then we have another way of seeing things that is highly complex that comes from the Slovenian group at the National Institute of Science in Ljubljana. And that is this model that takes into account a fact that we have a lot of processes that are taking place, but also that we might have electronic conductivity in our SEI. So that makes our models, these kind of transmission line models. These models have quite a lot of parameters, right? So I have something like 8 to 12 parameters that I have to somehow fix. So the chemical engineer in me says, yeah, that's fine, but the physical chemist in me says, no, it's not. I don't know what to do with 12 parameters, and I cannot measure them directly, so I do not know if the numbers that I get from this model are actually fitting. So this is the reason why I have been trying to do it a little bit differently, and there are two kind of extremes that I have been using in this case. And that is, either we try to fit, we have porosity and we have liquid channels. We either try to fit this model as a kind of one pore, one channel, and then try to imagine that we have many of these pores and channels in such an SEI. In this case, we have seen two cases. One is when we have very similar activation energy to the liquid, and then we will have basically simply the resistance of the bulk of the liquid in series with the resistance of the liquid in the channel and the capacitance of the bulk. And then it gets a little bit complicated if we have the activation energy that is a little bit higher than the liquid but lower than the solid, right? In the sodium electrolyte, we see really the switch from one case to the other. But what is important in these kind of equivalent circuit models is, as you see in red, the capacitance actually comes from the bulk. And this is also one of the reasons why this capacitance was off in these Auerbach papers in the mid-90s. So in that case, the capacitance was really not fitting to what we were expecting. But if we just take into account this porous bulk, then this is fine. On the other hand, we can just say, well, it's a liquid-solid composite material. For this, we had forever used our parallel switching model, where we have a total conductivity that is proportional to the conductivity of the liquid and the solid and their volume percents. In this case, the liquid is so much more conductive than the solids, orders of magnitude, that we can just approximate it with the volume percent of liquid and the conductivity of the electrolyte. And that gives us directly some estimate of the volume that we need in order to see liquid conduction, and that's very, very low in the case of magnesium electrolyte. So these are kind of two extremes. Okay, so for magnesium data, we have never seen these kind of very odd oddities in terms of resistance. We still see smooth curves, but this might appear from time to time, that you see, if you're doing this kind of investigation, that you see that the resistance change of your SEI in time is kind of odd. This is a sodium glyme combination. It has been reported as a very stable electrolyte for sodium metal. I agree, it is very stable in the first couple of hours or hundreds of hours, but then after that it becomes quite a roller coaster of resistances at the interface. And then you can also see these kind of drops. So what we try to do in this specific paper is try to, again, use the parallel switching model to try to reproduce these kind of growth phenomena of things filling into the pores. So if you're interested in that, it's also a little bit more complex impedance paper. You are very well. I would be glad if you read this paper. Anyway, so I talked about lithium and sodium, a little bit differences of magnesium. In the potassium case, it's also quite complicated. We also should have an oxide and superoxide, but also carbonate. This is also something that we should have on magnesium. And we expect much more SEI compounds than in the case of lithium and sodium. We started looking at these materials when Mariam was doing her PhD. She sits here in the first row. So she tried looking into the changes of the resistances in symmetric lithium cells after cycling and has observed a very strange behavior, and that is that the resistance drops. But that was not something that we expected from what we have seen in the growth case. So this was the beginning, and I talked about SEI growth under open circuit voltage conditions, but the next step is actually to understand what happens under cycling, because this is the real situation. We can, of course, build artificial SEIs, but we have shown that in the case of sodium, it doesn't really, we can never really make a fully dense SEI, even though if they appear so. So I see already Max standing up, so I'm going to fast forward to my conclusions. And that is that I hope that you're kind of convinced that we are now starting to understand the SEI growth both on alkali and alkaline earth metals under OCV conditions. The next step, as I said, is what happens under current. And I think for artificial SEIs, there is quite a lot of room for improvement. And my thanks goes to a couple of people working with me, and you're also invited to read some articles about some other topics that are not maybe related directly with metal anodes that are out recently. Thanks a lot.
Thank you very much.